Hello. So this will be the last video, hopefully, I think it is, for chapter 17. And I'm covering slides 53 to 59 or so. Some loose ends that we didn't really look at. It's more conceptual than anything, and you will need this to answer questions from for the last homework 3 from chapter 17. So I'm trying to record this today and have it available for you. Some of the things that we need to note about weak acid, strong base titrations versus strong acid, strong base. And you're learning a little bit more about this also through the the lab assignment, the titration worksheet that you're doing. Now, weak acids, remember, they are weak. So if you look at HF, this is a weak acid. So it's going to dissociate to give H plus and F minus. But being a weak acid, it does not dissociate fully. On the other hand, if you have a strong acid, it's going to dissociate completely. See that? So at the beginning of the titration, all right, at the beginning of the titration, let me bring a graph in here. I'm working on slide 53. Okay, that's 5.3. So I'm going to show a picture from slide 57. This is a strong acid, strong base titration. And just look at this one. This is a weak acid, strong base titration curve. Look at the differences. We are looking at initial differences. A strong acid gives off all its H plus ions. So the H3O plus concentration is higher. For the strong acid than for the weak acid. Right? The weak acid, look at this equation. It holds some of the H's and gives only a few. Here, it gives it all that it has. So H3O plus concentration, I'm going to put that with water so you see that it is actually H3O plus. We try to make it simple. All right. So you're going to have all of the HCl converted to H3O plus. In the case of the weak acid, only a few of those go into solution as ions. So you have more, you have less here. How does that translate in terms of pH? If you have more concentration of H3O plus, that gives you a lower pH to begin with. Here you have lesser amount of the H3O plus, so a higher pH to begin with. That's what they're talking about. That's this point that they're talking about. Because the weak acids do not release as much H plus as strong acids, weak acids will have a lower Ka value, and therefore they'll have higher pH values to begin with. Okay, we're talking about what happens initially. Now, I'm going to take two examples of a weak acid. This is weak acid 1, and this is weak acid 2. So this has a higher Ka than that weak acid. So initially, the concentration of H3O plus for weak acid 2 is going to be even smaller. So it's going to release very few H plus ions. Therefore, its pH initially is going to be the highest of these three. So that's what we're talking about. Strong acids, because they release all the H plus ions, they'll have the highest, they'll have the highest H3O plus concentration, but the smallest pH initially. And then as the Ka value decreases, their initial pHs will start increasing. Okay. I think that makes sense. Makes sense to me. Hope it does to you. Now going on to the next slide. Now they are looking at the initial rise in pH. Okay, so that's the next stage. We looked at what happens initially, right at the beginning. And then we're going to look at how this thing is almost flat here, and then it starts jumping there. But look at the weak acids. Looks like there's an initial increase. You see that? There's an initial increase. And it's more so pronounced here with the very small Ka value. It just increases and then it plateaus off. You see that? So that's what they're talking about next. The initial rise in pH. So weak acids are poor at resisting pH changes. Okay, they're like any chance they get, they are capable of increasing the pH of the solution. And weak acids with higher pKa values, that's what I showed you, have higher initial rises in pH. Higher pKa value equivalent to lower Ka values. So I'm going to show this diagram again and explain what I just said. So if you have a strong acid, there's not much of a change in the initial stages in pH, but as the Ka value, this Ka value is very high, okay, for a strong acid. So as the Ka value decreases, what we noticed was their initial pH in solution is high, and also you see an initial rise in pH, and this is more pronounced, like I said, until it hits the mid region before equivalence point is reached. Okay, so the mid region, let's say it's this region here. Okay, now here it sort of plateaus off, and it does plateau off there. Okay, so they're talking about what happens here. Initial rise. All right. So they're just describing the graphs one at a time. Now, what happens at the equivalence point? Okay. And this is specifically for a weak acid, a strong base, and a strong acid, strong base, that they are comparing. If it's a weak acid, remember, we wrote this down last time, pH at the equivalence point is greater than 7. Okay. Weak acids do not release as much H plus as strong acids. We know that, and that's why they are called weak acids. Now, why is it greater than 7? We also discussed this when we talked about, when we did the titration curve. I'm sorry, the titration, curve. And also we did the calculation of the pH at every stage of a titration. So let's say you have F minus as your weak acid. I'm sorry, let's say you have HF as your weak acid and your strong base is KOH. The products are K plus, F minus, and water, right? Now, at the equivalence point, moles, you'll have 0 moles of HF left and 0 moles of KOH left, and you'll have few moles of KF left. Okay. Now, K plus and F minus, K plus does not react with water. Because it comes from KOH. This is quite reactive because his source is HF, which is a weak acid. So F minus will react with water to give HF and OH minus. See that? So this is the reason why at the equivalence point, F minus reacting with water produces free OH minus ions. Therefore, the pH is greater than 7. All right, does that make sense? Okay, now let's look at, that's what is explained in this. The conjugate base of weak acids are more basic than counter ions of strong acids. So K plus is not reactive, but F minus is with water, quite reactive with water. Therefore, F minus will react with water to produce OH minus. K plus will not produce any changes with water. So because OH minus ions are being produced, the pH is going to be greater than 7. So if you look at the curve again, this is the equivalence point for the strong acid. This is the equivalence point for the weak acid 1. And this is the equivalence point for weak acid 2. You see that? So as Ka decreases, then the pH at the equivalence point is going to increase. Got that? As, I'm going to write it here, as Ka decreases for the acid, pH at the equivalence point increases. All right. That's what it's mentioned here. I know I wrote all over. Have higher pH values at the equivalence point. And as the Ka decreases, the pH is going to keep increasing at the equivalence point. Got that? I think I did this one. It's just a repeat. And one last difference. I'm on slide 56. Okay. So all the changes, what are the changes at 0 ml of base added? What happens initially, okay, after the addition of the base? And then what about pH values at the equivalence point? Next, we are going to look at, these changes close to the equivalence point. What are the changes just before reaching the equivalence point? Okay, just before reaching the equivalence point. pH change when you look at that for a strong acid, you see how it comes up, and then there's a pronounced increase. See that? With just 0.1 ml. That's what you see. You may have a slight pink color, nice and pretty, and then you add like half a drop or less, and then you see it hit the roof with the pink color. You see that? But let's look at what happens as the Ka value decreases. For weak acid 1, they call this, this big jump. I call it a big jump. Strong acid shows a big jump in pH. Here in this, they're calling it being a very abrupt change. Okay, they mean the same thing. Now, as you decrease the Ka of the acid, as the acid gets weaker, they're saying the pH change near the equivalence point is less abrupt. Okay, look at that of a strong acid. It goes from, I don't know what acid they picked, it goes from like pH 2.5, it jumps to, let's look at it here, like 10.5. Okay, at the equivalence point. That's a big jump. Let's look at weak acid 1. They're saying this is less abrupt. Let's look at the pH change. I'm going to say it starts at about 6. Okay. And then it ends at about 10.5. So your pH meter will jump from a pH of 6 to 10.5 when you use weak acid 1. Weak acid 2, they say this is less and less abrupt. And they say they have more elongated titration curves, okay? Goes like that. And then this range is so small. So if I need to quantify it, it's like 9.7 to, I don't know, it's like 10.5 to me. You see, for weak acid 2, that jump, there's no jump really. It just crawls from 9.7 to 10.5. You see that? So that's another difference. So when asked, you should be able to point out these differences. Okay? So a big jump for a strong acid, and as the acid gets weaker and weaker, the jumps get smaller and smaller. Okay. All right, I think that's, oh, there's a problem here. We have to do that. Slide 57, I already showed it to you. The problem is on slide 58. An equal amount, all right, of each of the following acids is titrated with a common base. Select the acids with the highest and the lowest pH at the equivalence point. Okay. Now, which acid has the highest Ka and which acid has the lowest Ka? Okay, so Ka, pKa is negative log of Ka. So if pKa is 4.75, what is Ka? So that will be okay. So you can calculate Ka values for these. I'm going to show the trend at the bottom. As pKa value increases, Ka value decreases. Okay. So which acid, I'm sorry, which decreases? So which acid has the lowest Ka? And which acid has the highest Ka? You can do numerical calculations, or I'm just going to use the trend. The highest pKa will have the lowest Ka. So I'm going to say the one that has the highest pKa will have the lowest Ka. And then on the other side, this is going to be benzoic acid. Okay. And now, what did we learn from the graphs? Which one will that have the highest pH at the equivalence point? So remember our trend. As Ka decreases, pH at the equivalence point increases. See that? The weakest acid will have the highest pH at the equivalence point. So which is the weakest acid here? This is the weakest. And so this will have the highest pH at the equivalence point. Okay, so that graph helps you estimate this. So find out in the list which one has the lowest Ka. So that's your weakest acid. And that will have the highest pH at the equivalence point. So this is the, of the three, the strongest acid. And this will have the lowest pH at the equivalence point. Got that? That was simple. As long as you understand the curve, then you're good. Okay, so try to understand graphs on slides 57 and 56, and then you should be good. And there are some questions from homework 3 that will do address these points that I've just talked about in this recording. All right, that officially ends chapter 17. So we'll have to start with chapter 18 on Thursday. Bye now.